Hello? Can you hear me now? Sorry. Yeah.
Yes,
but
I can.
I guess you understood everything anyway, because the slides are crystal clear. Yeah. Okay. So, but this is the form somehow that is a little bit nicer to work with for the self-adjoint case at least. So then. Now come finally some kind of definition. So we have an operator from H to H. A is self-adjoint, unbounded, and this is just bounded operators, a bounded rational function. So we define the domain of this will be the domain of A, independent on lambda. And that is quite important. So it's independent on the spectral parameter lambda here. And of course, we cannot define it for a singularity, so we take away this C1 to CL where we have the poles. Okay? And then I will define another problem, and in the next slide, I will show how they are related. So I will define a block operator matrix. I call it fancy A because we have two different A's here. Fancy A then is, as you can see, this have a somehow symmetric structure, where A is the same thing that we have here, and we have all this B1 to BL like this, and then we have a block, and this is maybe what is most special with this problem somehow, that this block here, C, it's just diagonal, have just non-zero terms on the diagonal, so it's some real positive numbers. So this is, of course, a very special structure that we can explore somehow. Okay, so why did I define this? Yeah, you will see very soon here. So if we now look on the spectrum of the block operator matrix A, we could think about that the spectrum is all lambda in C. We could take any lambda, such that 0 belongs to the spectrum of A minus lambda. So that will be the same thing. Otherwise, it's invertible. So this way of writing it go through for like any function. So the spectrum of S is all lambda in C, and we take away the singularities such that 0 belongs to the spectrum of the fixed operator S of lambda. So this is how you extend it from the usual definition of spectrum. Okay, so what about the connection between the two? Yeah, what we have here is a Shor-Frobenius factorization of this block operator matrix A minus lambda, and then you have this product with three terms, where the first and the last one, they are invertible. So if A minus lambda is invertible, that means that S is invertible and C minus lambda is invertible. So from that we could see that the spectrum of A, if it's properly defined, and we take away C1 to CL, then we get the spectrum of S. So they are closely connected, these two operators, which means, or the operator function and the block operator, meaning that we can study one of them and get information from the other. And sometimes it's better to study the block operator matrix, and sometimes it's better to study S. Okay, so the first thing is have to do with the block operator matrix, and we will have some assumptions. So we assume that A this entry, you have discrete spectrum, is self-adjoint bounded from below, and these BL are bounded. And later we will use that they are also injective, but we don't need that now. And then there are some general theory developed in a series of papers. I mentioned one here, but there are also others that tell us that the central spectrum of the block operator matrix is exactly this C1 to CL. And also, if we do it correctly, it can be defined as a self-adjoint operator bounded from below. What is maybe kind of most important for this talk is the last one. And this means that above the maximum of the central spectrum, we assume that they are, C1 is the smallest one, and then they are just larger and larger. Then above the largest value, we have a gap in the spectrum. So we have an interval above CL that belongs to the resolvent set. We don't know how big it is, but there is something. And that's very important. Okay? So if we now take the case where we have just one term. So we have the central spectrum will be C1, according to the general theory. We can define this as a self-adjoint operator. So C1 is in the central spectrum, so it must be an eigenvalue of infinite multiplicity or an accumulation point of eigenvalues, so because it's an isolated point. And we know that there's a gap above C1 from what I said in the last slide. So if we have an accumulation of eigenvalues, it must be from below to this point, C1. Okay. So now we need to exclude the possibility that this is an eigenvalue of infinite multiplicity. Then we have a small lemma. Let's say that the dimension of the kernel of this block operator minus C1 is smaller or equal to the number of eigenvalues of A below C1. So if we can prove that, we know that it's not an eigenvalue of infinite multiplicity because A was bounded from below also. So we can only have finite many from that. So, and a sketch of how you could do that. So first we just take some non-zero vector tilde with u and u hat in this kernel. We just plug it in to what we have there and see when it's equal to 0. And then we can see that if u tilde is non-zero, then actually the first component here must be non-zero, that we get from the injectivity that we assumed. And we also get that C1 must look like this, where we have the inner product here, so A, U, U. And this looks very much what we have for a mean-max principle, and that is actually exactly what is used. So in the second step, we somehow used mean-max principle for the first component of this. We do some projection and use this thing, and then you can get the bound, roughly like that. So I hope you can believe it's true. Okay, so now the main contribution of the paper was more what happened if we have many of these poles. And it turned out that it's happened exactly the same thing, kind of. So we will always have gaps above each of these poles. We will always, if all spaces are infinite dimensional, of course, we will have accumulation of eigenvalues to all of the poles. We also have some bounds, but we don't really use that. But so the point here basically is that we have quite good control of what happened. If we want to do more, we need to do numerical computations. But from an analysis point of view, we maybe cannot do so much more. We have like an idea how the spectrum look like. So and this was based on one paper with Heinz and Christiane, and they have done much more, as you may know, in this area. I cite a couple of papers by them, but actually the main paper for this this paper is the second one with Xavier and Matthias Lager. So it's based a lot on variation principles, but I didn't really go into that here. So, okay, so the self-adjoint case or no losses, we have quite good control of the spectrum. So what happens now if we don't have that? So what happens if we have a rational function of this form? I mean, before we had some constant and characteristic function, but in any case, this is a bounded operator that is bounded by 0. So we just put something there. It doesn't really matter. So now, of course, the spectrum may not be on the real axis, so we would like to know where it is. So we want to have some kind of enclosure of the spectrum. And then we could think about using this block operator matrix and do some perturbations. We will do that. And then I will also look on an enclosure based on the numerical range of the rational function. And then I will, in the end, also look on different formulation of Maxwell's equation actually give you different kind of bounds also. So you will see. So I will start with Maxwell's operator on now first order form. So we have both electric and magnetic field, 6 components. So here, six components. So this M here is sometimes at least called a Maxwell operator. And as you can see, the material property with this epsilon is hidden inside this F. And the only thing that differs is that you have an omega here instead of an omega to the power of 2. So that's the difference. Yeah, we assume that we have chosen everything, so it's self-adjoint and nice, this M, I mean. Okay. Now we do exactly the same trick as before, where we split we write the characteristic function, multiplication operator as a product. And I will consider a case when we have just one term. I drop all indexes, so I don't have like a 1 and so on, everything. And I put C equals to 0. It doesn't really matter, but yeah, I did that for this presentation. And we do, as I said, the same thing as before. V star will be the characteristic function. We write then this minus omega times epsilon, which was this rational function, as a other form of rational function, a transfer function. And if you just multiply and so on, you can see that this is exactly minus omega times this, I mean. Okay, so we, and I call this R. This thing that we have here is R. So, okay. So now comes some magic. Yeah, the first part is maybe not magic, but so we had this factorization before with three terms where 2 of them were invertible, and we have the same thing here. What we do is that we extend R by D, and then we have this identity here where the outer factors are invertible. So the spectral properties of this guy and this in the middle, they are the same. Okay. If we now look on the operator function itself, we had this Maxwell operator and something with the material properties. Now we actually write this as one matrix. So it will look like this. It's exactly the same thing as before. And then this one here, we call that R. So this will be R, or R of omega. It will depend on omega, of course. And then I call them this X, Y, and Z. And then you can do something similar. This is why I said this is magic, but you can do something similar here. You extend with a D, but then we have done some reformulation of some computational reasons. And you can see then that you can see that the spectrum of this block operator matrix after this extension is actually the same as the spectrum of this one. And yeah, have to believe me. So, and then it looks like this. So you can prove that, of course, it's some technical computations, but yeah. Okay, so now this is the problem I would like to work with, which is equivalent to working with this problem. This is the idea, except certain points.
So this is a congruence, not similarity.
Isn't it?
Yeah. This block on the left is not the inverse of the right, but adjoint.
Yeah. Okay. Yeah. So.
Similar, non-similar is okay, but to complete spectral properties.
They should have exactly the same spectral properties. I certainly hope so. Otherwise, we did something wrong. Sorry.
If this was just matrices,
Yes.
then that would mean that the R and D together, the spectral properties are the same as A, B, B star D.
If you take away certain points, you don't think it's true?
Vectors are different for sure.
Yes, yeah, vectors will be different. Sure.
It's complexes.
Yeah, okay, yeah, so okay. But the spectrum, that's all we care about right now. Okay.
When they prove these Rees basis properties, Alexander Marcus and so on and so forth, I mean for these structures, you don't have, these R and D are self-joined, but then you have congruence, then you no longer have orthogonality, but you have a Rees basis property. Is that where it comes in, or
You-
just slide too far away?
If you think about Alexander Marcus, then they usually have these polynomials and this kind of linearization. This is not exactly the same type of linearization, but it's related. So this is from one of our papers. So yeah, exactly. But it's certainly not new in like that. But they work with these companion polynomials and companion matrices and look. But it's not exactly that. But of course, it's somehow you introduce some new variables and stuff. And if you want to. Yeah. So but now we don't care about that. We just care about the spectrum. Only I care about this. So the point with all of this messy computation was actually to get something where we could get first something that we could define as self-adjoint. You can see it's have symmetry at least, and some kind of perturbation. So that was the whole point with all of that. So why we bother? I mean, in principle, you could also somehow write this as a polynomial by multiplying and then do another type of linearization. But I'm not really sure if you would get this kind of structure there. I don't think so. I'm quite sure you don't, actually, when I think about it. So, but here we have in the form with self-adjoint and a perturbation. Okay, and then we will use, actually the first thing you go to is, of course, Carter's book, but then it's turned out that Cernin and Trette, they did something as well, a little bit more recently, 2016, and I will not go through this, but I will show a picture, how it looks like for a concrete case, and it could look like this. So I will use this several times. The spectrum could be in the white areas. So here to infinity in this direction, in this like gap here, and to the right. But it cannot go below 0.2 in the imaginary part for the constants and stuff that I have used in this plot. Okay, so that is what we get from the general theory, but of course we have a very special structure. I mean, these theorems are for general self-adjoint problems. So maybe we can do a little bit more since we have a special structure. And yeah, we will actually use the numerical range. And as you probably know, the numerical range is usually huge if you look on an operator. So if you look on this block operator matrix, I mean it's both the self-adjoint and the perturbation, and look on the values you get out if you apply this to a vector in the domain and take the inner product with you. This is a big convex set. So this will not help us. But we can do the same thing with the operator function. And then what's different is that we need to solve this kind of problems. So it will be a function on omega here. So it will be something we can solve for each u. And this set also should contain the spectrum, at least the closure as usual. And it will not be some big blob that is convex, but it may not be connected or so. So it might give you some more information. Okay. So now, so this is for a kind of general case. That's why I use a different notation here. But I think it's maybe easier to think about it in a general case. So if we have an operator function with some function times the identity, I never write out the identity as you have seen before. So we have some function of omega. We don't talk about exactly how they can look like, but kind of arbitrary. A1 and A2 are self-adjoint. And then we know then that omega is in the numerical range if this is 0. And we can write it out what it means in terms of operations on A1 and A2. Okay, but of course it's not so easy to understand how this looks like because we work with U in an infinite dimensional space. So instead of doing that, we replace these inner products with just any number from the numerical range of the individual operators. So let's say alpha 1 belongs to the numerical range of A1. Replace this part, and alpha 2 belongs to the numerical range of this. This will certainly give us some enclosure. Might be bad if we have two unbounded operators, but in our case here we have one unbounded and one bounded, and it turns out that it works nicely. If you have two unbounded, you need to include some relation between them, otherwise this will be useless. But so the enclosure is that we solve this equation here, where alpha 1 and alpha 2 belongs to this set. So we have some kind of rectangle. Not so sophisticated bound, it seems, but it's actually still quite useful. And we will now look on the case where we have, that we looked on before, we have this constant c was equal to 0, and we have now the first order formulation, meaning that we have this curl like this. So the first order formulation, second order formulation was with two curl after each other, and the first order is like this. Okay, so the numerical range for this, this could be anything on the real axis, and the second one will be something between 0 and 1. So this is the given values, and then you need to analyze the zeros that we get from this enclosure. And if we do that, we get this. So the spectrum and the numerical range as well should be inside these red curves. So anywhere here. And then, of course, if we also add that they cannot be in the gray areas, we have a little bit smaller domain. Okay, so now we use this first order formulation of Maxwell's equation, and then the question is, can we do better or worse if we use the second order? And then if we compare these two, so what we just had was for A omega. This was for the first order formulation. And the second one, the second order is with the hat. So the only thing that differs is that we have here we have omega to the power 2, omega to the power 2. And of course that M in the first case, when we have this block operator matrix, the numerical range could be anywhere. I mean, it's just R. And here it's bounded by 0 to infinity. So it's smaller somehow. Okay, and then you can actually prove that the numerical range, I will show you an example next slide. So the numerical range, or the enclosure of the numerical range using the second order formulation will always be inside the enclosure of the numerical range of the first order. This is not difficult to prove, but I will not do it here. So, okay, so in practice, it looks like this. So if you use the second order formulation, we know that the spectrum must be on this line segment that is on the imaginary axis, or here or here. So this was for one case. It can look a little bit different. In some cases, I tried these gray areas that we have from the other bound actually helps a little bit. So we have some intersection between them, but here we didn't really benefit from the previous results. Okay, now if we add some numerical computations, this is actually just 2D stuff, but it's valid also for the full Maxwell's equations. But so this is for one example, and then you can see these dots here are eigenvalues, and you can see that you seem to have a lot of dots down here. Could be some numerical problems, or it could be that we actually have an accumulation of eigenvalues. And we will prove that, not completely, but we actually can prove that there is an accumulation of eigenvalues there, and this is what I will talk about in the last part of the talk. And then we will reformulate everything in terms of bounded operator polynomials. And use quite old results actually. It was factorization results from operator polynomials that started with Klein and Lange, but there were many papers. Gochbay have some, but then these three guys here had a lot of papers on this. So, okay, I will give some reference in the end. So, okay, if you look on the general case factorization of operator polynomial, just remember, I mean, we had a rational function, but if you just multiply, we get the polynomial, and then we needed to do a lot of, we need to do a few things with these polynomials to get it on the right form, and I will not really go into that, but if we have a general polynomial, P, and then we hope that there exist two polynomials, Q and R, where you can see that R have a special structure. So you have this parameter K here. So K will be important. K will be in later 1 or 2. So it's a low order polynomial. We hope that this kind of polynomials exist that actually splits the spectrum in two parts. So this one with the low K take care of the spectrum inside some region gamma, and Q take care of the rest of the spectrum. Okay, so then we call this a spectral divisor. Somehow we splitted the problem in two parts, one for Q and one for R, and we only care about R. So, okay, so how do we actually know that we have a spectral divisor? Yeah, and then there is, of course, this is not our result. This is also from the general nice theory, and it says that if we, maybe I can start with the pictures actually. So this is plots of the numerical range for certain cases, and what we hope for is that we have an isolated part, like this one here, where we have a dotted line around that separate this from the rest. It should be bounded, and the point of interest should be inside. So this point is the point of interest here. And we have the same thing in a couple of other cases. Okay? So this is what we hope. This is one, and then we should have exactly k roots of this inside this numerical range, part of the numerical range. So if we can show these two, then we know that we have a spectral divisor. So we know that we have this polynomial, this one with a certain k. This is rather technical, I think, at least, but I hope the main points go through. Yeah. So okay. So if we now have this kind of problem, we multiply with the denominators, we get the polynomial and so on. Then in the case when k equals to 1, spectral divisor of order 1, then you have this in a series of papers. Some of them are in Russian. I just looked on Alexander Markus' book, which I would cite in the end. Then we can prove accumulation of eigenvalues if we have these special conditions. So actually, the resolvent of A0 needs to be very nice. It should be in a Shatterford-Neumann class. Otherwise, it will not work. And then we should prove that, that we have this spectral divisor of order 1, and this was related to properties of the numerical range. So the challenge is basically to show that we have this separated part, which I showed in 3 pictures before. And then another smaller problem is that k could be 2 sometimes. And it will be actually be 2 if we have a double root of this thing here. Then it will be of order 2. So we have at least some results here, and the first thing is that it's not so difficult to see that if A0 is large enough, then all the possible parts of the numerical range, so if you have like a quadratic polynomial, it will be 2, that is the maximum, and so on. So everything that could split will split if A0 is large enough. But of course this, so then you can say something, but then you need to assume that it's large enough. And if you want to do something more explicit to tell us what is the large enough, the value for that, then we could only do that for if L is equal to 1. Then we still have like a polynomial of degree 4, which is still a little bit, I mean, when you multiply, then you still have a little bit nasty calculations in front of you. So we could also prove for k equals to 2 or larger by doing some perturbation argument, compact perturbation argument, and they didn't do that, but you could see this maybe as a small exercise. So they in this book or these papers they only consider k equals to 1. So okay, so not so many details, but that was the main ideas. So if we now look on one concrete problem again, or picture, how this looks like, then we use these bounds of the numerical range, which in this case is down then these red parts here, like this, and we have poles at these 2 points. This is these ones here, and we could then prove accumulation of eigenvalues, and numerically you get a lot of eigenvalues close to these poles. So this is how you see it.
What do you use to solve? Do you solve the compact or?
Yeah. Yes. Okay. So now final thing. So what we had now was something in of this type with Maxwell or whatever it is, but the important fact was that we assumed that TA is could be an unbounded operator, self-adjoint and blah blah blah, but B here should be bounded. Then everything will be depends the domains and everything. It will just depends on TA. If you take this Moore-Gibson-Thomson equation, as I said, that are used in high-intensity ultrasound, it should also be nonlinear then, of course, but the linearization is called that. Otherwise, you usually add one more name. And it's a little bit funny. So we started to look on that. You can see that we have 3 derivatives in time, 2 and 1, and no derivatives. And we have a memory term. And we have 3 different unbounded operators, TB, TA, and TC. This means that the domain will definitely depend on the spectral parameter, because these operators, of course, they cannot be general. I mean, there must be some relation between them, otherwise this is not well defined. But they will cancel out, usually, at certain points, which means that we need to define it on the whole space. I mean, if we take away all the unbounded operator, we need to define it on the whole space. So this is a big difference. That is what I wrote there in the end. So, but again, I jump very far. So this is just one case how it could look like. So we have just all of them are actually the same. All are just a Laplace operator. This is in 2 dimensions for the simulations. So I compute eigenvalues and hope that they are correct. But this is more for illustration than showing something about the numerics here. So the blue circles, this is eigenvalues. And then you have also eigenvalues here, but they are very close together, so I blowed it up a little bit. And you can see an accumulation to a certain point. And this is a point you can actually explicitly compute. And it's this one, I guess, 0. Blah, blah, blah. And then we also have the same thing here. It's a little bit larger, but you also have an accumulation to a certain point, which you can determine explicitly for this case. And yeah, a few more you can also do a little bit more. Okay, so this was based, the second part, on Axel Torshage's PhD thesis. So he finished a couple of years ago and work in the industry now, unfortunately. But of course, the big names here, I said we started with Klein and Lange. We have a paper by Branco and Branco, also about, this is, sorry.
GUS.
Aha, okay, I need to update them. I mean, many of these papers works with quadratic polynomials. Alexander Markov's book contains a lot. And if you want to read more during the summer, you can go to the 370 papers that are cited there, and then, yeah, it should be enough. So, thank you very much.
Any questions? Or are there any questions online?
How you discretize this on page 28?
28.
No, 20, that one before, yeah.
This one.
Or 24, anyway.
Okay. This one.
Yeah, why are only to what? How you made the...
Okay, so what we actually have here, I mean, since this is rather general, I mean, this is for a photonic crystal application. So this is just periodic boundary conditions. It's discretized as usual. I think here it was actually used DG method, but it doesn't really matter. So nothing special, if you say like this. The nice thing here is, of course, okay, this block operator matrix having a central spectrum seems scary, but the operator function is a Fredholm function. So we actually have nice theory for this. If we, I mean, so now this was just Laplace. So it was just Laplace for this one here, because I looked on but it doesn't really matter for the bounds, of course. Here, so I mean this was just for, so we have these TE and TM polarizations in 2 dimensions, and then it actually boils down to type of Helmholtz type of problems.
But the question was, I mean, this is highly structured and it's easy to fall off the bounds due to round off or something or you know.
But for the essential spectrum, you need some, but once you discretize, it's gone.
No, but
So you have something different to get the essential spectrum.
no, I mean that's what I meant. That I mean, if we look on, yeah, if we go from beginning somehow, yeah, something like this. Then this problem, we have convergence theory for that one. So, sorry.
For min-max or?
No. I mean for Fredholm valued functions. So here we know how we have no essential spectrum, but we have singularities. But outside the singularities, everything is actually quite nice, I think. So and of course for the block operator matrix, then we had an essential spectrum, but I mean. If it works for that one, it should also work for reformulation of that one.
Complex arguments.
Sorry?
You have complex arguments.
Yes.
And you know, I mean, Volcker made a whole story about, you know, computing these arguments which have to be exactly symmetric all the way through, and then you build the structure of your linearization so that you get that and no other possibility. So, I mean, do you need to do something like that here? Or, I mean, you know,
No.
very
No.
and still you nail them exactly.
You mean like here?
Yeah.
No, it's nothing special. I mean, they are probably not exactly on the imaginary axis, I would think, but they are very, very close, so we cannot see that. Yeah.
I think that was what you meant, you know, how...
Yeah. No, but you're right.
Because there, unless it's really this, you have all these symmetries exactly, so as it being exactly on...
But I mean, what I usually do, at least, I mean, I enforce the symmetry somehow. So.
That's what he says as well. Write everything down and let the linear algebra enforce...
Yeah. So maybe they actually are more or less exactly on the axis when I think about it. Because, I mean, the bounds apply to any case. So as soon as the matrices are symmetric in the way they should be there, it has nothing to do with that it's a differential operator of a certain type.
But for me, it's probably for me.
Yeah. Yeah, I understand. I understand that. Yeah.
Because, you know...
But that's why this is a talk in applied operator theory and not numerical analysis.
If you did, say, plane wave expansion and separation of variables, then I would trust, of course, you compute it. But then simple things can be enforced also algebraically and still get the same...
No, but I mean, I mean, simply if you take, you can take the most crappy discretization that you want here. M is completely wrong, simply, but it have the right symmetry, and the same thing with other. Then it should satisfy. So the values that I have here might be completely wrong. but all the matrices satisfy the conditions such that the bounds are valid. Maybe this is the way you should put it.
In a sense, this linearization that you showed of rational function which Bai used for fluid-solid interaction, I mean, that's a brilliant linearization which preserves the structure you could lose if you were to turn it into a polynomial linear problem.
You mean, do you mean for the non...
Before.
The
One, yes, that one.
This one, yeah.
So, I mean, you know, there, if you were to go into a polynomial version, you could, I mean, and turn on a non-self-adjoint solver, you couldn't be, you know, all over the place. But here it is very self-adjoint, and you use a self-adjoint solver for that, and by guarantee, all your eigenvalues will be real.
Yeah.
Or imaginary, depending on.
Yeah. Here they are real.
And if you were just to multiply it out, and I think that's the point that he made, George and Bai, because the same problem you get in fluid-solid interaction there, these beads are projections onto, like he had these cylinders floating in liquid, and then B is an L2 projection onto a cylinder.
Okay.
So you have a sum of them all, and then of course you can do it like a polynomial problem, and then you might not, anyway, you have artifacts, and if you do it like this, first of all you're faster because you're using a symmetric solver, and then you have other nice guarantees.
Yeah. Just the last comment, I mean, here, I started with the Fourier transform. What we used here is the Laplace transform, so that's why it's on, so it's a little bit different. And of course, this type of problems relate very much to what I work with Luca now, what we do, and with Stefano also. Then we work on time-dependent problems and try to use spectral properties also. So,
And Stefano did a very nice DG.
Yeah, in MATLAB that we can play around with. Any other questions from, maybe from, no?
It is a problem for people online because they hear you but they don't hear us.
Yeah.
So out comes the question, then you start answering and
I should repeat the questions, of course. I didn't think about that.
I'm hoping that the mic has a good pickup.
Yeah. Okay.
Okay, thanks.
Thanks.
So should we
Thank you.